Dear students, today we are starting the fourth module. In this module, we will learn about two-dimensional electronic systems like 2D MOSFETs, heterostructures, quantum wells, modulation top quantum wells, etc. And today we are going to cover MOSFETs and their energy band diagrams. So you may be familiar with the MOSFETs, that is metal oxide semiconductor FETs. So here is P-type silicon substrate, N-type source and drain, and this is the gate. The gate may be metal or polysilicon, conducting polysilicon. This region, that is metal, then thin oxide and P-type semiconductor, that is a substrate. So this is an equivalent MOS capacitor. There is two conducting layers. They are separated by a dielectric material. By default, there is no channel between source and drain. In this case, if we apply a sufficient positive gate voltage, there will be accumulation of electrons just under this thin oxide layer. That means an N channel is created between source and drain. Now we can see the basic working and energy band diagrams. First we can check the flat band condition. That is the ideal MOS capacitor with zero applied voltage. This is the reference vacuum energy level. Vacuum level means it is the energy of electrons outside of any material. That is the highest energy reference level for an electron. In ideal condition, we will draw the Fermi level as a constant flat line for metal, oxide and for the semiconductor. It is represented as E suffix F. So the Fermi level, it is the highest energy level an electron can occupy at absolute zero temperature. Okay. Then the energy required to take an electron from the Fermi level of metal to the vacuum level, and it is given as Q phi m. This phi m is the work function. So it is the minimum amount of energy to remove an electron from the metal to a point in the vacuum level. Okay. Similarly, this is the work function of semiconductor, and in the ideal condition, we have taken as phi m is equal to phi s. Then oxide, it is wide band gap material, it's an insulator. So this is the conduction band and this is the energy of valence band. Then in the semiconductor region, since we have taken P-type substrate, the valence band energy level, that is EV, it will be very close to the Fermi level. And this is the conduction band energy level, EC, and this is EI, intrinsic energy level. That means it is a Fermi level position in the band gap of an intrinsic material, EI. So this condition is called the flat level condition. And there is no accumulation of charge in the metal or in the semiconductor. Now the next case is accumulation. Here a negative potential is given to the gate. So the energy level is shifting upward. Energy is given as Q into gate voltage, that is charge into gate voltage. The charge of electron, that is minus Q, multiplied with negative gate voltage, which is equal to QVG. So it is moving upward. In the oxide also, the energy is shifting upward. So there is bending. When you give a negative gate voltage, the holes will be accumulate here. So at the interface, the valence band, it will move upward and it will move very close to the Fermi level. The EC and EI, they will move away from the Fermi level. So it will bend in this direction. So here you can see the accumulation of holes, and here the negative gate voltage at the metal. So the electric field, it will have a direction like this. Okay. Next is depletion. That is, if we apply a very small positive potential, in this case the semiconductor band, it bends downward. Since you are giving a positive gate voltage, the holes at the interface, they will move away or it is get depleted. Here you can see the valence band, it is moving downward. Similarly, the EC and EI, they are also bending downward. On the metal side, since the gate voltage is positive, the energy will be minus Q Vg. That is negative, the energy is shifting downward. And the electric field direction, it is from here to here. Next is strong inversion condition. Here a large positive voltage, it is applied to the gate. Here the band bends very sharply. That means since you are applying a large positive gate voltage, more and more electrons that will be attracted and they will accumulate at the interface. So the conduction band, it will move downward and it may reach the Fermi level or very near to the Fermi level. So on a p-type substrate, an electron layer is created and it is called the channel. Here it is n-type channel. So the p is inverted into n. That's why it is called an inversion layer. And this layer will provide a conducting channel between source and drain. So the electrons can move through this channel between source and drain. If you check the energy band diagram, and due to this sharp bending at the interface, more electrons will be trapped here. Since the electrons are trapped, the electrons' movement across this direction, it is also confined or restricted. So the movement of electrons is confined within this well, potential well. Since the electron movement is confined across one direction, these trapped electrons are called 2D electron gas, two-dimensional electron gas, accumulation of electrons within the well, potential well. If you reduce the channel size, it will become a 2D system. So the potential well that is formed at the interface, it is triangular well. We have already seen this triangular well in the first module. Okay. Anyway, since the electrons are trapped in this well, the possible energy of the electrons due to the electric field applied can be taken as E suffix n. That is the energy of electron across the Z axis. Here we have taken the movement of electrons across this Z axis as restricted. Since it is a 2D system, the movement across other two axes, that is movement across X and Y, it is not restricted, free movement. And we know that the energy of electron is h cut square k square divided by 2m. Therefore, the energy of electron in xy plane is h cut square kx square divided by 2mx star plus h cut square ky square divided by 2my star. M is the effective mass of electron across x and y respectively. Therefore, the total energy of the electron in the triangular well, it is taken as En plus, that is a restricted energy, plus energy of electrons through xy plane. Okay.